Today I want to share with you a problem that I first learned about back when I was in 8th grade and attended an astronomy club, or more precisely, a telescope building club run by Leonid Leonidovich Sekhruk. And one day he brought to our club meeting an issue of Sky and Telescope magazine with an article about the Crab Nebula. And in this article there were two photographs of this nebula, taken several decades apart. And we too will take two photographs taken with a significant interval of time between them. The first photograph was taken in 1950 with the best telescope of that era at the Mount Palomar Observatory, and the second was taken in 2000 with the Hubble Space Telescope. Both photographs are aligned using the fixed stars. And look, if you switch from the first photograph to the second, you can see that the Crab Nebula is expanding right before our eyes. And those who first discovered this expansion said to themselves, well, if that's the case, then it looks like the Crab Nebula was formed as a result of a giant cosmic explosion. And this explosion happened by cosmic standards quite recently, and we can calculate approximately what year it occurred. Let's mark several distinctive spots in the filament structure of the Crab Nebula on a photograph from 1950. And then we'll mark these same spots on a photograph from the year 2000. And it turns out that over 50 years, all the characteristic distances have increased by about 5%. And this means that the explosion of the Crab Nebula occurred about 1,000 years ago. That is in the year 1000 AD, give or take a few decades. And it turns out that in July of the year 1054, Chinese astronomers observed a bright star in the constellation of Taurus in the morning sky. This stellar event was visible for an entire month. And so, astronomers learned that the Crab Nebula is made up of vast, intricate gas streams flying out in all directions at a truly tremendous speed, formed as a direct result of a powerful supernova explosion that was observed almost 1,000 years ago. And of course, it would be incredibly good to know at what precise speed these energetic streams are expanding and exactly how far they have traveled in a full 1,000 years. If we knew the accurate distance to the magnificent Crab Nebula, then, of course, knowing its precise angular size, we could accurately determine its true, immense size. And so on, following this logic. But for now, we don't know the distance. However, we do have the possibility to work backwards. If we knew the speed at which these streams are expanding, we could determine both the size of the nebula and its distance from us. And then Leonid Leonidovich took another photograph out of his briefcase, which showed the spectrum of the Crab Nebula. Here you should pay attention to this bright double line. In fact, this is one of the lines of singly ionized oxygen, with a wavelength of 3,727 angstroms. And it's split into two lines because of the Doppler effect. The far side of the nebula is moving away from us, and its spectrum is shifted toward the red, while the near side is moving toward us, and its spectrum is shifted toward the blue. And the splitting of these lines amounts to 30 angstroms. And now we can set up a proportion. The splitting of the line by 30 angstroms relates to the actual wavelength of the line, which is 3,730 angstroms, in the same way as the doubled velocity of the gases, because we have gases moving toward us and gases moving away from us, and the splitting corresponds to this doubled velocity, relates to the speed of light. And accordingly, from this proportion, we find that the velocity of the gases is 4,000ths of the speed of light, or 1,200 kilometers per second. And since we found the velocity, we can also determine the size of the Crab Nebula. After all, its expansion has been happening over 1,000 years. So we just need to multiply 1,000 by 4,000ths. And we find that the characteristic radius of the Crab Nebula is about 4 light years. And accordingly, its diameter, though it is somewhat elongated in one direction more than the other, is, well, in any case, its typical size from edge to edge is about 8 light years. And now we can also determine the distance to the Crab Nebula. From Earth, it is seen at an angle of 5 arcminutes, which is 1/700th of a radian. And this means that the distance to the Crab Nebula is 700 times greater than its size. We estimated its size to be 8 light years, so the distance to the Crab Nebula is about 6,000 light years. And at this point, the story about what we did back then in 8th grade with Sekhruk comes to an end. But of course, there is still a lot of interesting information to share about the Crab Nebula. Well, first of all, astronomers ask themselves, if these expanding gases really did result from a supernova explosion, then what remains of the supernova itself? Is it possible to spot some object at the center of the nebula that is the remnant? Well, there really are two faint little stars there, and in 1942, Bade actually, well, not exactly identified, but at least concluded that nothing contradicts the idea that one of them is neither closer to us nor farther from us than the nebula itself. And it could very well be that very remnant. Well, the very next significant part of this fascinating story actually takes place in the momentous year of 1968, when a powerful radio telescope was precisely pointed at the renowned Crab Nebula. And it was then definitively established that somewhere deep inside the vast and enigmatic nebula, there is indeed a distinct radio source that consistently pulses at a remarkably precise frequency of exactly 30 times per second, a truly astonishing astronomical phenomenon. And in 1969, a year later, it was discovered that it also pulses in the optical range. And here, astronomers have conclusively concluded that the incredibly dense remnant of this powerful supernova is a rapidly spinning neutron star, measuring only 20 kilometers in diameter, which astonishingly rotates around its own axis at a remarkable frequency of 30 times per second. So in essence, it's quite similar to this high-speed wave. And from this distant luminous star, something akin to a powerful focused spotlight is continuously directed outward. And this intense pulsating spotlight is precisely pointed in our general direction 30 remarkable times per second. The next remarkable image of the Crab Nebula was obtained in 1999 by the Chandra Space X-ray Observatory. Here you can see many details that were not visible either in the optical or even more so in the radio range. In this image, you can see jets shooting out from the pulsar and complex toroidal structures around it. And of course, the Crab Nebula will serve as the source of many more discoveries in astronomy and astrophysics. And now I want to ask you our traditional closing question. How is it that the neutron star at the center of the nebula makes 30 rotations per second, while ordinary stars, take our sun for example, make one rotation every 25 days? Share your thoughts on this in the comments to our video on YouTube.